Hey, welcome back. In this video, we're going to continue discussing how to prove things. In the last video, we saw several rules of deduction that you can use to make individual steps within proofs. In this video, we're going to see some basic methods that you can use to carry out whole proofs. One of the methods that we'll see, the one we'll start with, is called direct proof. We'll also see a method called proof by contraposition. We'll also see one that looks similar called proof by contradiction. For all of these methods, we will see examples of how to apply the method to prove some simple statements. We'll also see a method called exhaustive proof and proof by cases. And we'll see two others. Existence proofs, we'll actually see multiple kinds of existence proofs, both constructive existence proofs and non-constructive. And we will see a uniqueness proof. So let's start with direct proof. When we have a direct proof, we are proving some proposition P implies Q. And the method is to start with P and use rules of deduction until we reach Q. Here's a simple example of a direct proof. We're going to prove that if n is a power of 2, then so is n cubed. N cubed is a power of 2. So first, we'll use the definition of n being a power of 2. If n is a power of 2, then we can say that n equals 2 to the k for some integer k. We can also say that if n equals 2 to the k for some integer k, then n cubed equals 2 to the 3k for that same integer k. Here, we're just using properties of exponents. Now, we can conclude using the last two bullets together with transitive implication that if n is a power of 2, then n cubed equals 2 to the 3k for some integer k. So again, we use the last two bullets together with transitive implication there. And recall, transitive implication says that if we have some proposition P implies Q, and we have some other proposition Q implies R, then we can conclude that P implies R. So that was the transitive implication right there. Now we can also say if n cubed equals 2 to the 3k for some integer k, then by definition of being a power of 2, n cubed is a power of 2. So all we use for that one is just the definition of being a power of 2. But we can take that proposition together with the proposition in the last bullet. So these two together now, and we can do another application of transitive implication. So we can use this transitive implication rule of deduction twice. We use it right here as well. And those two together tell us that if n is a power of 2, then n cubed is a power of 2. So it might seem like this proof we did a bunch of steps to prove something very simple. And it's true. We did write out our rules of deduction, and we did several steps for something that most of the time when we prove it in a real math paper or even on a problem set in this class, I would not expect you to write out that many steps. So this kind of statement, you could write it out in a single line. But here we're being extra careful to illustrate the rules of deduction in some simple proofs. But we won't be that careful for most of the proofs in this class, even in this video. So here is another proof method. This one's called proof by contraposition. Again, we're trying to prove a proposition of the form P implies Q. So our premises are P and our conclusion is Q. And we're going to start with not Q and try to use the rules of deduction until we reach not P. And the reason why this will allow us to conclude P implies Q is because not Q implies not P is logically equivalent to P implies Q. Another name for a proof by contraposition is an indirect proof. So here's an example. Prove that if n squared is not a multiple of 3, then n is not a multiple of 3 for integers n. So we're going to use a proof by contraposition for this one. We will suppose that the integer n is a multiple of 3. So what we did is we took this proposition right here and we negated it. So we had n is not a multiple of 3. Negated, it became n is a multiple of 3. Now, if we know n is a multiple of 3, then we can say that n equals 3k for some integer k, just by definition of being a multiple of 3. And we can square both sides. We can say n squared equals 9k squared, which equals 3 times 3k squared for some integer k, the same one in the last bullet. And that means by definition of being a multiple of 3 that n squared is a multiple of 3. So we got n squared is a multiple of 3 right here. And notice that that is the negation of this right here. So these two, there's a negation between those two. Just like these two, there is also a negation. So we started with not Q and we obtained not P. And that lets us conclude that P implies Q. In this specific case, we conclude that if n squared is not a multiple of 3, then n is not a multiple of 3 for integers n. So the next method has a very similar name to the one that we just did. This one's called proof by contradiction instead of contraposition. In this case, we're trying to prove a proposition P. We're going to assume that not P is true, and we're going to use that to derive a contradiction of the form Q and not Q for some proposition Q. And the reason why this implies that P must be true is because the proposition not P implies Q and not Q, it is logically equivalent to P. So here's a nice example of a proof by contradiction. We're going to prove that the sum of any rational number and any irrational number is irrational. Now notice here we have any, and over here we have another any. So we're saying for all rational R, let's say, and for all irrational J, we're trying to conclude that the sum R plus J is irrational. So it's a statement with two universal quantifiers. If we want to do a proof by contradiction, we will assume that it is false and use that to derive a contradiction. Assuming that it's false, we suppose for contradiction that not for all is true. So we suppose that the negation is true. Remember, not for all is the same as exists, not. So we suppose for contradiction that there exists an R, a rational number R, that's our first exists, and there also exists an irrational number J. So here our first exists, our second exists, such that R plus J is rational. R plus J is rational here, and notice up here R plus J is irrational. So this one right here is the negation. It's a negation of this one up here. Call that star, negation of star. So that's our assumption, and we're going to try to get a contradiction from that. So we assume that R is rational, so we'll work with that. We know that rational numbers can be expressed as the ratio of two integers. So we can say that R equals m over n for some integers m and n. We also assumed that R plus J is rational. So we can assume that R plus J equals x over y for some integers x and y, just like the last bullet. And we can use those previous two bullets to conclude that J equals R plus J minus R by definition, because the R's cancel there. And that equals x over y minus m over n using the last two bullets. So these two give us this. And x over y minus m over n, we can make common denominators and put it all in one fraction. We can write it as xn minus my over ny. And those are all integers there. Xn minus my, that's an integer. Ny, also an integer. So J is rational. But we assumed that this J was irrational. So it's both rational by definition of rational and irrational by our assumption up here. So that gives us the contradiction. And so there does not exist a rational number R and an irrational number J such that R plus J is rational. So our assumption right here is false. And another way to say that last bullet down there, in other words, we can say the sum of any rational number and any irrational number is irrational. So the next type of proof is not going to seem very interesting, probably. It gets more interesting if you involve computers. So when we use this type of proof called the exhaustive proof, we're proving some proposition with a universal quantifier over some finite universe. So we're proving something with only finitely many things to check. And what we do is we check all of them. We just calculate every single possibility. Usually, when we do interesting exhaustive proofs, like in some modern math paper, if there's an exhaustive proof, usually it will use a computer. And we're going to see an example of an exhaustive proof that does not use a computer in this video. But the problem that we look at for this proof could easily be generalized to something that would use a computer. So here's a little background on the proof. We'll define a prime number, p greater than 1, as a positive integer that is only divisible by plus or minus 1 and plus or minus p. So those are its only divisors. No other integer divides it. I want to just emphasize p is greater than 1. It's an integer. So p cannot be equal to 1. And there's a list of the first few of the primes: 2, 3, 5, 7, 11, 13, 17, 19, and so on. So here's something that we could do with a simple exhaustive proof. Prove that there are 8 primes less than 20. And in order to prove that, you can just list the numbers out from 2 up to 20 and check if each of them is a prime. And you can use that list that I just gave you, or you can check it yourself. And you can see that the primes on that list that are less than 20 are 2, 3, 5, 7, 11, 13, 17, and 19. There are 8 of them. So that's something you can prove with a simple exhaustive proof. And the same type of problem you could generalize to something that you would use a computer for. For example, if you want to count how many primes are less than some given number n, and you can easily generate a list of primes. So another type of proof method that we're going to see an example of is a proof by cases. This is another one where we're trying to prove some proposition with a universal quantifier, and the universe might be restricted. And when we do a proof by cases, the idea is that we split our universe into different subsets, and we handle these subsets using possibly different proof methods. So for example, and this is an interesting problem that I found on Stack Exchange. I actually changed the problem a little. So the original problem was only about A and B, I think. And this is just a simple variant that works with a similar method. So the problem: suppose that A, B, C, D, and E are real numbers for which A is less than or equal to B, is less than or equal to C, is less than or equal to D, is less than or equal to E. Also suppose that A plus B plus C plus D plus E equals 5. And prove that A plus B plus C is less than or equal to 3. So this one, there's a nice way to prove it using only 2 cases. For the first case, suppose that C is less than or equal to 1. Since we know that A is less than or equal to B is less than or equal to C, this implies that A plus B plus C is less than or equal to 3, because A plus B plus C is less than or equal to 3C. For the second case, we just need to handle when C is greater than 1. In this case, we know that since C is less than or equal to D is less than or equal to E, then D plus E is greater than or equal to 2C, which is strictly greater than 2. And since D plus E is greater than 2, we can combine that together with the fact that A plus B plus C plus D plus E equals 5. And these two together imply that A plus B plus C is less than 3. And that finishes the problem. We handled all possible cases because the C can either be less than or equal to 1 or greater than 1. So we only have 2 more types of proofs that we are going to look at in this video. But one of these types of proofs will actually see multiple examples of it because there's multiple ways to do it. And that type is the existence proof. So when we're doing an existence proof, we're proving some proposition that has an existential quantifier. And like I said, existence proofs can be constructive or non-constructive. And let's first look at a constructive example. So with constructive examples, if you're proving some proposition with an existential quantifier and you're trying to construct an example, you just need to find some element of the universe which satisfies the given existential proposition. So you need to find a witness for that existential quantifier. So that's all you do with a constructive proof for some proposition with an existential quantifier. You just have to find some element of the universe that makes that proposition true. So for this problem, we're going to prove that there exists a natural number, n, with 100 less than n less than 1,000, that is both a perfect square and a perfect cube. And these words, if you haven't seen them before, the definition of perfect square is n equals a squared for some integer a, and perfect cube means n equals b cubed for some integer b. So we want to prove the existence of some natural number with these properties, that it's between 100 and 1,000, not inclusive, and it's both a perfect square and a perfect cube. So in order to do a constructive proof for this, we just have to find such an n. Oftentimes, if there's only finitely many elements in the universe, for a constructive proof, we can just search through all of them until we find one. And this is an example where we can just search through all of them. We can get a computer to do it. And we see that 729 is equal to 27 squared. And also 729 is equal to 9 cubed. And furthermore, 100 is less than 729 and it's less than 1,000. So that tells us that there exists a natural number between 100 and 1,000, not inclusive, which is both a perfect square and a perfect cube. And we prove that constructively. So now that we saw a constructive example of an existence proof, let's see a non-constructive example. So we're going to prove that there exists a digit 1, 2, 3, 4, 5, 6, 7, 8, or 9 that occurs infinitely often in the decimal expansion of E. And I want to note what we're proving here in this first bullet. The same statement holds if you replace E with pi or any other transcendental number that you like. So first, I'd like to note some things that we already know about E, and we will take these for granted. We'll assume that they are already known. So these will not be things that we are proving in this video. First thing that we know about E already is that E has infinitely many digits to the right of the decimal. And that's because E is an irrational number. So if E only had finitely many digits to the right of the decimal, if you think about it, that means immediately that E would have to be rational. So if we know that E is irrational, that tells us that there has to be infinitely many digits to the right of its decimal. Now, for this non-constructive proof, it's actually going to be a non-constructive proof that also uses a proof by contradiction. So we already talked about proof by contradiction earlier. So we're going to use that here and that together with a non-constructive proof. So here is the proof by contradiction part. We're going to suppose that all of the digits 1, 2, 3, 4, 5, 6, 7, 8, and 9, we suppose that all of them occur finitely often in the decimal expansion of E. So let's compare that to what we're trying to prove. We were trying to prove that there exists a digit 1, 2, 3, 4, 5, 6, 7, 8, or 9 that occurs infinitely often in the decimal expansion of E. So that statement up there, we're saying there exists some digit, and down here we're saying for all. And we can think about, why does that make sense? Well, up here we have exists and then something in parentheses. And all we did was negate that. When you negate that, it gives us down here a for all, not, and whatever was in parentheses. Now, what was in the parentheses up here? There exists some digit 1, 2, 3 up to 9 that occurs infinitely often in the decimal expansion of E. And then not what's in the parentheses. We're saying for all of those digits 1, 2, 3 up to 9, we're saying they do not occur infinitely often in the decimal expansion of E. And not occurring infinitely often is the same as occurring finitely often in the decimal expansion of E. And that's what we're going to suppose. And we're supposing that for the contradiction. So that's going to be our goal here. We're going to try to take this assumption that all of the digits 1, 2, 3, 4, 5, 6, 7, 8, and 9 occur finitely often and use that to get this contradiction. So if we know that all of the digits 1, 2, 3, 4, 5, 6, 7, 8, and 9 occur finitely often in the decimal expansion of E, that means that each of them only has a finite number of occurrences. So it means we can look at all of their occurrences in the decimal expansion, and we can see what's the rightmost occurrence. So I can draw a little picture here. So we can have our decimal expansion of E. E equals 2.7182818, and so on, ... And we can look at the occurrences of 1, 2, 3, 4, 5, 6, 7, 8, and 9 in here. And we can look all the way out to the rightmost occurrence. So we can say the last occurrence, we'll say R right here. We'll say that's the rightmost occurrence of any of those digits, 1, 2, 3, 4, 5, 6, 7, 8, or 9. And we know there has to be a rightmost occurrence because there's only finitely many occurrences of each of those digits. So we can just look at all the occurrences and see which one is furthest to the right. And there it is. I've drawn it right there. So that's the last occurrence of the digits 1, 2, 3 up to 9 in the decimal expansion of E. And what we know about that is if that's the last occurrence of the digits 1, 2, 3 up to 9, then all the digits after this in the expansion are just zeros. So we know E has infinitely many digits. So if that's the last digit that's 1, 2, 3, 4 up to 9, well, the only digit left is 0. So everything after that to the right has to be zeros. And that tells us then that another way we can write E, we can write it in a simpler way like this. E equals 2.718, 2818, and we can write all these digits here all the way up to that R. And then after that, we don't have to write anything else. We can just terminate it right there, and that's E. So if all the digits after that R are all just zeros, then we can write E where there's only finitely many digits after the decimal. So we can write E in a way where it terminates after the decimal at some point to the right of it. And that gives us a contradiction. So the contradiction specifically is if we have E written with finitely many digits to the right of the decimal, so we wrote E like this, that tells us that E has to be rational because we can write E as a fraction where the denominator is some power of 10. So we just showed that E is rational. And this is a contradiction because we know already that E is irrational. That was our assumption. It's something that we're taking for granted. We didn't actually prove it in this video, but it's something that we assume we already knew before. So we showed that E is rational. We know it's actually irrational, and there's our contradiction. And since we have a contradiction, that allows us to conclude that the statement that we assumed in order to get that contradiction must be false. And that statement was all of the digits 1, 2, 3 up to 9 occur finitely often in the decimal expansion of E. So we know the opposite of that statement, its negation, is true. In other words, there exists some digit 1, 2, 3, 4, 5, 6, 7, 8, or 9, which occurs infinitely often in the decimal expansion of E. And that finishes the proof. So again, it was a non-constructive proof. We did not find the digit. So we did not construct the digit. We don't even know what the digit is. All we did is we showed that that digit has to exist. So non-constructive. And again, the other thing I want to emphasize here is that we also used a proof by contradiction. So the proof by contradiction was also a major part of this proof. Now, one more basic method of proof that we're going to see in this video, and that is a uniqueness proof. And uniqueness proofs, we're going to see a bunch of these in this course. And you're also going to see uniqueness proofs in other math courses, depending on the courses that you take. And for the most part, they're going to look very similar. The method you're going to use in these kind of proofs, it's going to be pretty much the same as the one that you see in this video in the next few bullets. It's going to be in a bunch of different contexts, but really the method, it's going to look very similar for the most part. So with the uniqueness proof, you're trying to show that there's only a single x in the universe for which p of x is true. So we talked about quantifiers in last week's videos, and we talked about the uniqueness quantifier. So we're trying to prove there exists unique x such that p of x. This is what we're trying to prove when we're doing a uniqueness proof. And what we do is we assume that p of x is true, and we assume that p of y is true for some elements x and y in the universe. And then we show that x must equal y. One other thing we must show for uniqueness proof is we need to show that there actually is an x in the universe for which p of x is true. So remember, with the uniqueness quantifier, you have to have exists x, p of x. You must have that true in order to have uniqueness. So it's possible for exists x, p of x to be true and to not have uniqueness. But if exists x, p of x is false, then you definitely cannot have uniqueness. So here's a simple example of a uniqueness proof. And we'll see other more interesting ones in later videos. Prove that there is a unique integer x such that 2 to the x plus 5 equals 21. So we'll suppose that we have 2 to the x plus 5 equals 21, and 2 to the y plus 5 equals 21. That implies that 2 to the x plus 5 equals 2 to the y plus 5, using the transitive property of equality. And subtracting 5 for both sides give us 2 to the x equals 2 to the y. We can also take log base 2 of both sides, and that gives us x equals y. And to show that there exists an x in the integers for which 2 to the x plus 5 equals 21, we can just say that x equals 4 works, and it does. And that implies what we're trying to prove, that there is a unique integer x such that 2 to the x plus 5 equals 21. So that brings us to the end of this video's methods, but we will see many other proof methods in later videos. So some other methods that we'll see are induction. We'll see both weak and strong induction, and we'll use this in a bunch of different kinds of proofs. We'll also see the pigeonhole principle. This is very useful for proving bounds in different kinds of counting problems. We'll also see generating functions. This is very useful for counting things. We also will see some specific inequalities, which are useful for proving bounds in combinatorics problems. We'll also see that recursion can often be very useful for taking combinatorics problems and boiling them down to recurrences. And we'll also see some other methods for doing non-constructive existence proofs, including some probabilistic methods. But those will be in later videos. So that's all for now. Thanks for watching.